What? So here we go. Here's the warm-up for today. Welcome back, everybody. Sorry I couldn't make a video from yesterday. Are you asking the person through the computer if they want a bite of an orange? No, I'm good. Yeah, thanks. Appreciate it. Warm up. Juan wants to rent a house. He gathers data on many similar houses. The distance from the city center, X, and the monthly rent, Y, are shown in the scatter plot. Now, I will tell you right now, this is a release question off of a test. I can't remember what year it was, but this is an actual test question. Okay? Based on the scatter plot, what could 1275 represent? Noah? What'd you say?
Wait, what was this? 1275 could represent, let's see here. There's no 1275, but...
Right, that's true, but what could it represent? You raised your hand and you don't even know what it's asking.
It represent rent.
Okay. You're right, it could represent rent, right? So A could still be an answer. B could still be an answer. Now, the estimated change in distance. Could D be an answer then? No. So I can knock out D right away because that's distance. Okay. So what do we think our answer is? What do we think our answer is? A. I would agree with A.
When in doubt, go.
No.
No,
when in doubt, go with the best answer.
No, when in doubt, you go with C.
No. When in doubt, go with the best answer.
If you're, I'm not doing all my tasks.
All right. So let's kind of go through the rest of the. Let's go through the rest of the answers to see why they are incorrect. Now, why is C wrong? Well, what are they referencing here? The estimated change in rent. That is the slope. Right? That is referencing the slope. Am I going down 1275 for every mile I go out? No. So C is out of the way. Now we have to decide between A or B. The estimated minimum rent for a house far from the city. Now, as I go far from the city, what should happen to the rent? It should go down. So something far from the city should not be all the way up here. Right? That's why B is not an answer. The estimated rent for a house in the center of the city, somewhere close to the center of the city. Yeah, that makes sense. 1275 is up here. Questions about that? Jim.
Since there's just like no dots for like 10 and 12, does that mean that like they just don't have to pay rent?
No, that just means they didn't have data out there.
So like it's like less, is it like less than 200 or like?
We don't know. Based on this trend, we can assume that it might keep going down. Shh, gentlemen.
Did you bring pizza for lunch?
Yeah.
Sorry, that's kind
Well,
of
like,
cool. I was just wondering what it was. That was a bagel.
Like you said, they might not have like
data out there.
Oh, it does. Actually.
Oh,
They
like
might not have even collected that data. We don't know. This is only just a little snapshot of what's going on.
Yeah, that would be a steal.
All right. Let me answer these questions. What do we have questions over 1 through 6 from the homework? Are there any questions 1 through 6? No, I will definitely go over 9. But do we have any questions 1 through 6?
I just have a general question.
Okay.
So when you're describing part C for 1 and 2, is that when you say what the correlation is, positive, negative?
Yeah.
Okay.
Yeah. You can say it as it's increasing or decreasing, but we'll try to push ourselves to say more positive, negative correlation.
Okay, I just wanted to make sure.
Yeah.
It goes up and it goes down.
Yeah, that's technically what positive and negative correlation are.
What you want to say, like increasing, decreasing?
Yeah. Okay. All right, let's take a look at number 9 then. The table shows the total amounts Y in thousands of dollars of money after a homeowner saves, table shows the total amount Y in thousands of dollars of money a homeowner saves on electric bills X years after installing solar panels. Okay, so let's graph this and see what kind of trend I have. Now notice that I go into negatives. That might have thrown some people off. You might be thinking, wait. This can't go into negatives, but it can. And here's why. If I'm at year 0, I just installed the solar panels. Those solar panels probably cost me a lot of money, didn't they? How much money do you think it cost them?
A lot.
Based on the table, $12,000.
Oh, yeah.
That's probably what it cost them for installation and everything, was $12,000. That's why it's a negative, because they are in the whole $12,000. It's going to save them money on their electric bill, but it's only going to save them money in the long run. Okay, so let's graph it and see what that looks like. So my x values are going up by 5s, 5, 10, 15, 20, 25. My y values, I've got to go down to negative 12 and all the way up to 28.4. So let's go by 10s. So this is a 5. Let's go by 10s. 10, 20, 10, 20, 30. All right, so this is 10 here. Always mark at least one spot on there so I know what the scale is. 0, negative 12, somewhere down here. 5, negative 5.2, so somewhere right here. 10, 3.8, so somewhere up here. 15, 10.5, just above my 10 line. 15, this is 20, 20, so right at my 20 line there. And then 25, 28.4, just below my 30 line. Okay, do we see a linear relationship? A pretty strong linear relationship too, right? One that looks like it's pretty close to a line. Okay, let's pick this point and this point as my two values that I'm going to choose. That is 0, negative 12 from the table. And this is, okay, what is it? 5, 10, 15, 20. 20, 20. I don't know if I chose the exact same ones. Actually, no, I chose 15, 10.5 in the key. Does it have to be exactly the same? No. I mean, trust me, I just sketched this graph pretty quickly. So it's not going to come out pretty accurately, but that's okay. We're just going for ballpark figures because we're working with statistics.
Do you have to put arrows on the end of the line or no?
For statistics purposes, you can go into generality, so we can say, yeah, you can go anywhere.
Okay.
Yeah.
I kind of looked at like both of the last two numbers on the y and x, and that's how I did it.
Both the last two numbers on the y and x.
Like I did 28.4 minus 20 and then 25 minus 20.
Oh, you just did these?
For my y2.
No, I'm gonna come back to you in a second because I want to see what your slope came out to be as it relates to my slope. So 20 minus a negative 12 gets us 32, and then divided by 20 minus 0, which is 20. What did you get for your slope?
1.68.
See, it's very, very close, right? No matter what 2 points we pick along this line, the slope is going to be pretty close. Somewhere around 1.5, 1.6, 1.7, something like that. Did anybody get any different? What did the key say? 1.5. Yeah. So somewhere around there, 1.5, 1.6, 1.7.
I got 1.34.
Okay, that's good too. Honestly, I would probably accept anything between 1 and 2. So,
Okay.
I only got 0.9.
which 2 points did you pick?
I did 0, 12, and 20.
Wait, I just did that one. How'd you get that?
Oh, because it's both negative, and I put it as a
Oh, you put it as positive, yeah.
Yeah.
Okay, so let's keep going here. Letter A, write an equation that models the okay, so we have m, y equals 1.6x, and the nice thing that I like to do is pick the y-intercept, 0, negative 12, because we just have to go minus 12. Whenever the y-intercept is close to being on the line, choose the y-intercept. Interpret the slope of the y-intercept. What is the slope? What is that 1.6 representing? What is the slope representing in the context of the problem? Good. How much money you're saving per year. So accurately, we could say you're saving about $1,600 per year on your electric bill by doing these solar panels. What does the minus 12 represent again? Kind of talked about it earlier. What's that? Good. $12,000 spent on the solar panels. All right. Let's take a look at section 4.5. Now, if you have friends in Honors Algebra 1, they did section 4.5 very, very differently than we are going to do section 4.5. And I'll talk about why here. In terms of what you need to know for the test, section 4.5 actually in the book, if you look at it in the book, teaches you how to use technology and a data table like we have on the board right now. Teaches you technology and the data table to create that equation a little bit more accurately than just picking 2 points. Because you know how there's some variation on all of our equations that we chose? There is no variation when you do it with technology. So, but you don't need to know how to do that for the test. All you need to know how to do is determine how strong relationships are together. Like, for example, everybody look up at the whiteboard for me. And you know what? Since I'm doing this on a video, I'll put it up here. Everybody take a look at these 2 scatter plots. Both positive, right? Is one stronger than the other? Yeah. We can see that. We could see that pretty easily, right? We can see that the second one is a lot stronger than the first one. But how do we talk about that? How do we define what is strong? How do we define that? And that's what we're going to be looking at today. That's what we're going to be talking about in terms of what's called a correlation coefficient. This term, correlation coefficient, goes with how strong our data ties together, how closely our data fits to a line. Yeah.
So it'd be like the stronger the line, the more.
Yeah, you say it as the stronger the correlation coefficient, the closer the data fits to a line. Yeah. So to everybody take a look up on the board here. The correlation coefficient is usually used with the letter R. Now, we will not learn how to calculate the R value in here. We saved that for Algebra 2. Like the Algebra 1 students, they learn how to calculate the R value. You don't have to do that on the state test, so we're not going to teach you that right now. What you do have to learn is what it means. What does the R value actually mean? The R value actually means the strength of the correlation. Here are the parameters on R, the correlation coefficient. It can range from -1 to +1. Those are the possible values that we have for R. -1 to +1. The closer you get toward 1 or -1, the stronger the correlation. So, in terms of the diagram that I drew on the board here, this second graph that I drew, this second scatter plot, would have a stronger R value, which means it's closer to 1. Okay? Now, the reason I say it's closer to 1, +1, is because it had a positive slope, because it has a positive correlation. If it had a negative correlation, it would just be a negative sloping line. It would have a -1 R value, okay, or a negative R value. The closer you get towards 1 or -1, the closer those points come into line. The further and further you get to 0, the more spread that data gets. Okay, let me show you a visual representation of this. Okay, everybody take a look up at your paper, or take a look at the board or at your paper. You see these diagrams down below there. Okay, this is just giving you all different types of R values. Notice that if you have a 0.95 or a -0.95, the strength of that correlation is exactly the same. So if I said to you, I've got one correlation that's 0.8 and one correlation that's -0.8, and I asked you which one was stronger, what would you say? You'd say, that's a trick question, because they're the same strength. Just one's positive and one's negative. What does that mean? That just means, well, positive sloping line or negative sloping line. As one goes up, one goes down, or as one goes up, the other goes up. Okay? That doesn't really have any effect on the strength of the relationship. That just has an effect on the direction of the relationship. So a negative 0.9 and a positive 0.9 are the exact same strength. Just one's positive and one's negative. The closer and closer you get towards 0, the more spread out the data is. The less and less likely you can see a pattern or a trend. Like, for example, in 0.6, do you see the upwardly sloping trend in 0.6? Yeah. But if I drew a line in there, there's going to be a lot of spread off that line. Okay? If I looked at negative point, I can see the negatively sloping trend generally. But those points are pretty far spread out. Any more spread out, and I might not be able to see that type of trend. Okay? The closer you get towards 0, the more spread out the points get. So I'm going to deviate a little bit away from your guided notes here to show you some actual released test questions. So, for example, this was, I remember when this one happened. Select all of the correlation coefficients that represent the linear model with a weak correlation. Is there some easy answers, and then there's one kind of tricky answer.
Yeah, this is my birthday.
What's that?
You made this slide on my birthday.
I did. That's true. November 16th. Was that the day I was not here? Yeah, because that's the day we were doing these slides. Everybody take a look. Now, how would you characterize a weak correlation? Well, you would say something that gets closer to 0. So can anybody give me an easy answer of a weak correlation?
The third one.
The third one, negative 0.103. Yeah, I would definitely say that's a weak correlation. There's one more easy answer. Yeah. 0.204. Now, negative 0.982. That's a strong correlation, right? So I'm going to leave that one unchecked. 0.907, strong. 1 is a perfect correlation, right? They line up exactly. There are no deviation away from that one. I don't love that they put an answer on there so low. Because the year that this came on the test, they were like, I didn't know what to choose. Is that really a weak correlation? Well, I guess you have to decide, well, it's weaker than negative 0.982, right? But is that necessarily, how would I characterize a weak correlation? So we actually looked it up. The state characterizes a weak correlation on anything in between negative 0.5 to 0.5. Okay? So they would characterize this as a strong correlation. So this box gets left unchecked. Okay? If they had an answer there of 0.495, you would check that box because that's a weak correlation. Anything between 0.5 and negative 0.5, they would characterize as a weak correlation. So these are our answers here. We would leave this one unchecked. Let me show you another state-released question. Brian collects data on the depth of a river at various points and the velocity of the river at those points. His data have a correlation coefficient of negative 0.9382. Which scatter plot could represent his data? Bryson and Brian. Apparently they changed the name there. Yeah, what do we think?
A.
He says A. Now, let me first start off by saying this. This R value, that correlation coefficient, tells us two different things. What two things does it actually tell us? One thing. That it's a strong correlation. Next thing. That it's negative. I should see a negatively sloping line. Okay, if it's a negatively sloping line, this one's gone, this one's gone. Well, and what about B? I mean, that's like no correlation at all. I hope my answer's A. Okay, yeah, I do see a pretty good, strong, I drew my line off there, but I do see a pretty strong correlation. They're pretty tight to that line, and it is moving in the negative direction. Yeah. Good. So my answer would be A. Good. Okay, jumping back to the guided notes now, we're going to talk about correlation and causation. Now, the wording here is going to be a little tricky. Okay, when you talk about the difference between correlation and causation, you have to be very careful. Correlation just means two things tend to go together, right? We learned about correlation yesterday, where two things are going to generally go together. When one thing happens, the other thing tends to happen with it. Are there counter examples? Are there outliers? Of course, and we expect to see that, and that's okay with correlation. When I start talking about causation, that's not okay anymore. I cannot have outliers. I cannot have a counterexample. When one thing happens, the other thing must happen with it. Like, I think, didn't we use the example yesterday of I work more, I get more money, right? As long as we are having an hourly rate, right? Yeah, that's true. Okay, let's take a look at some examples here. Time spent exercising and the calories burned. Okay, now, first thing that we have to decide is there some sort of correlation? Is there a correlation? Yeah. Is it positive or negative? Positive. So we can say that there is a positive correlation. Now we have to be careful here. Let's analyze the situation. Now we have to see, is this truly causation? Because if it's correlation, you have to check causation. Does one thing cause the other thing to happen?
No.
I would say yes.
Some exercises burn more calories than others.
That's true, but if you are exercising, are you burning calories?
Yes.
Yes. And that's the thing. Maybe at different rates, but is one causing the other to happen? If you are exercising, are you burning calories? Yes.
How would it ever be correlation? They're always going to be like that.
Okay, so let's talk about that. You can have let me put it this way. If you have correlation, there's a possibility of causation. Okay? If you have correlation, there may or may not be causation happening. So causation can't happen without correlation already. Okay? So that's why we say if it's correlation, now we have to take one step further and check causation. So we say there is causation here.
So like with the money thing, like the hourly rate.
That's a positive correlation and causation. Okay. Like for example, let's take a look at the next one here. The number of banks and the population of that city. Okay, if I increase the amount of population in a city, what tends to happen to the number of banks within that city? Should go up as well. So we say another positive correlation. Another positive correlation. You could do this with like drugstores too, right? Positive correlation. Okay, if it's a positive correlation, let's check causation. If I increase the population of a city, does that force more banks to open? Not necessarily, right? You could have a city with a lot of people in it that may have only a couple banks. So there are counterexamples, there are outliers, there are anomalies. So we say it's only a positive correlation and there's no causation. Okay. Let's take a look at C. The amount of organic food you eat and your test scores.
I don't know how that works.
You have to make your brain think more.
I guess it depends.
It depends. See, and so we would say no correlation. Maybe you are going to be the person that studies organic food eating and test scores. Maybe you might find there might be some sort of correlation. That's what statisticians get paid to do.
Less chemicals, more tests.
I mean, maybe you never know. Is there some sort of correlation? Figure it out. Okay, so we would say no correlation. So do we even need to check causation? No, because there's no correlation. We can't have correlation without causation. The other way. Okay, now here, this goes right back into the example that we talked about yesterday. Time, and we're going to assume that this babysitter is working at an hourly rate. Time spent babysitting and the amount of money earned. Positive or negative correlation? Positive correlation again. Right? Positive correlation. Is there causation? Yes, this is causation. Okay. We were actually talking out in the hallway. We were like, what's another causation example that we could use? And Mr. Parker said, the number of Big Macs you eat and the calories you are intaking. That's causation, right? You're eating more Big Macs, you are definitely gaining calories. right? You're definitely eating calories. Yeah.
Can you have correlation with a negative? Or sorry.
Yeah,
negative-
causation with a negative. Yeah, we just didn't have an example here.
Oh, okay.
Yeah.
What is it?
I don't know. But I would like to do the rest of these before I talk about something. All right, let's talk about this next one here. Now, this is not on your guided notes, but I wanted to show you an example of a release question that has causation and correlation. A store manager records the total visitors and sales in dollars for 10 days. The data is shown in the scatter plot. Look what we have here.
It's not mine.
A spam call.
That's mine.
Somebody spammed you.
You answer.
All right. Look at what we have in the table here. The number of visitors and the total sales. Okay, what should we expect to see? And when I say what should we expect to see, I'm talking about correlation. What type of correlation should we see?
An increase in visitors and increase in sales.
Right. Increase in visitors, increase in sales. Now, is that a causal relationship?
No.
Causal for causation.
No.
I would say no. Because could you walk into the store and walk out with nothing? Yeah, that's possible.
Or you can walk in and
Right, that would be awkward, but yes, right?
I feel terrible.
But if you walk in the store, do you have to buy something?
No. Just
No.
shoplift.
You could walk in and walk out if you really wanted to. So let's take a look at our options. An increase in sales causes a well, that's wrong anyway. Increase causing a decrease?
No.
That would be like a negative one, but this is not negative, this is positive, right? So we can knock out C as well because increase, decrease. Now, the only two options left, an increase in visitors causes an increase in sales. That is not correct because I use the wording of cause or causation or causal relationship. I'm saying the word causal right there. Causal. Not casual. Causal relationship.
Causal?
Yeah, that's the describing. That's like the adjective word of cause.
Oh, casual too.
No, casual
Flip
is.
the S and
Wait, no, you put
Flip the S
my
and
bad.
So B is out, so it should be D. Let's check. An increase in visitors is correlated with an increase in sales. That is true. That is definitely true. Yeah. Okay.
Not necessarily.
I mean, I like the. I was trying to think about it as we were going. The example of the more miles I drive, the gas left in the tank, because that I would say should be causal. Because if I drive more miles, the gas tank will go down. You know, you can't change that. There's no counterexample to that.
What if you have someone in the back riding and just has a gas tank just jump?
We could always do a bunch of what ifs. Let's look at this last example with the last 3 minutes. Shh, shh. Let's look at this last example here. This is what you have on your page. This is actually a throwback to yesterday because I know a lot of people didn't do number 9, so I wanted to put one more on there like this one. Okay, we got Miss Musto opened a new coffee shop. She recorded the number of customers she served between opening it and noon for the first 20 days of business. Everybody, right now, draw in your line of best fit. Draw in your line for your scatter plot. Now, everybody look at the options that you drew that are given to us. What can you estimate the y-intercept to be?
20.
Somewhere around 20.
So A and C are automatically off.
So A and C are gone. But what we have to figure out now is what is the slope? Well, I'm given a bunch of data points. Let's try to pull out the slope. Let's pick this point and this point. Now, are we given the table of values with these points? No, we have to estimate what these points are. So let's say these are going by 2.5 each box. So this is 2 comma, let's make that 25. And then let's say this looks like it's 9 comma 38. You know, we are just estimating, and that's totally okay. We're trying to figure out whether the slope is going to be 2 or 1.
13 minus 7 is 2. So it would be
So 38 minus 25 over 9 minus 2.
13 over 7.
13 over 7.
Just under 2.
It's 2. We can just do that.
Yeah, it's 1.9 if we round it.
Good stuff today, Mr. Lowry.
So we would say
B.
B is my answer. See, that ties directly into what we were learning yesterday. See, there are times when they're not going to give you the table of values. You have to kind of create that from the graph. Use your testing skills to knock out some other answers to narrow it down a little bit. Everybody say bye to the video.